Good morning. Thank you for joining our presentation. My name is Jeong, and I'm from UNIST, South Korea. Today, I would like to present our work, Bayesian code diffusion, for efficient automatic deep learning program optimization. Before we begin, I'd like to provide some background context. So deploying deep learning models across diverse hardware is not easy. So deep learning compilers were introduced. They take a model from various frameworks and generate code that optimizes on the target hardware. This slide shows how a deep learning model becomes executable code. One important step here is auto-tuning. Auto-tuning is the process of automatically exploring multiple implementations. It aims to find the one that have optimal performance on a specific hardware. To begin, let's look at one of the most prominent auto-tuning framework, Ansor. Ansor automatically generates many candidate kernels, iteratively tunes them, measures their latency, and keeps only the fastest. As a result, the code it produces can outperform even well-optimized vendor libraries such as BLAS, cuBLAS, or cuDNN. So let me briefly introduce Ansor's auto-tuning process. First of all, let me introduce Ansor's sketch, lure, and the parameters. Ansor builds its own search space by this keep component. A sketch is basically a sequence of optimization steps. Each step and rule represent a specific optimization step, such as loop split or loop reordering. These rules are applied based on the parameters, which are the concrete value chosen for each step. So in short, the code is optimized by applying rules and along with their parameters. This below figure shows an example of the split rule, also known as multi-level tiling. In this case, the parameters are set to 16 and 4, which means the inner loop we iterate 16 times and 4 times respectively. What's important here is that even though the rules stay the same, changing the parameters can drastically affect performance. That's why searching for the best parameter is such a critical part of Ansor's auto-tuning process. And let me briefly introduce Ansor's auto-tuning process. First, Ansor split the deep learning model into a set of subgraphs. For every subgraph, Ansor first builds a sketch or high-level template that is red dashed box in the slide. Think of each sketch as a set of optimization rules. The catch is that these rules don't have parameters, so Ansor still needs to find the optimized parameters. Once the search space is ready, Ansor pick one subgraph and start tuning it. First, Ansor pick one sketch from the possible sketches for that subgraph. Then it randomly sets the initial value for the parameters defined by the sketch's rules. Finally, it fine-tunes those parameters using evolutionary search to find the best performing configuration. The generated program candidates are first filtered by the cost model, and then the selected ones are measured on the target hardware. This whole process keeps repeating until the search time budget runs out. This process enables auto-tuning to find high-performance tensor program, for example, low-latency tensor program. But the vast search space hinders an efficient search process. For example, the parameter search space defined by a sketch, let's call it capital theta, is made up of all possible combinations of parameters for each rule in the sketch. In other words, it's the product of the parameters for each rule in the sketch. This makes it more challenging to achieve a high-performance tensor program within the constrained compilation time. This challenge opens up a few opportunities to make auto-tuning more efficient. The first opportunity comes from ignored subgraph similarity. Deep learning models are often built by stacking the same layers or blocks over and over again. And this slide shows the subgraph belonging to the BERT architecture. Most of them have same operation and batch matrix multiplication. Because of that, many subgraphs in this model look quite similar, and sometimes they have similar search space. But currently, the search space are treated as completely separate. Each one gets explored independently, even if they are almost the same. If we leverage the similarity of search space, we will be able to explore them much more efficient. The second opportunity comes from how fine-tuning is initialized. When sampling programs, Ansor randomly pick a sketch from the possible, and the Ansor randomly pick a sketch and also randomly set the parameters. Because of that, the tuner often need many fine-tuning iterations to reach a good result. If we can reduce random selection or random initialization, we can reduce the fine-tuning iterations. To take advantage of these opportunities, we propose a method called Bayesian code diffusion. The goal of Bayesian code diffusion is to speed up the compilation time by leveraging these key opportunities. And this table compares many auto-tuning methods relative to Ansor. And this method offers several improvements over Ansor related to the opportunities we discussed. For example, if there are a check mark in the first column, it means the method leverages subgraph similarity. And if there are a check mark in the second column, it means they improved the program sampling process. Many existing work have improved on auto-tuning process relative to Ansor. But when compared to ours, it advances all these aspects while supporting online learning and ensuring applicability across CPU and GPUs. So let me introduce the idea of Bayesian code diffusion. The idea is very simple. In this figure, each ellipse means the search space for each subgraph. And if the subgraphs are similar, the ellipse search space tend to overlap with each other. So once we find well-optimized parameter for one subgraph, and we propagate that onto other similar subgraph. So instead of starting from scratch every time, we can optimize it much more efficiently. We call the subgraph that share each parameter the prior subgraph, and the one that receives it the posterior subgraph. Now, I would like to introduce how the Bayesian code diffusion works. This is an overview of the Bayesian code diffusion. The first step is subgraph clustering. Subgraphs with similar structures, for example, ones with the same operators, often generate the same sketches. So we group them into a cluster, which makes it easier to propagate parameters between them. The second step is subgraph selection. This is an example of the subgraph in the same cluster. They are structurally similar, and the table shows their operations and tensor dimensions. Even within the same cluster, subgraphs can differ in their tensor dimensions. So when selecting a prior subgraph, we consider the tensor dimensions. In particular, we wanted the prior subgraph to be the one most similar to the others. So we calculate the cosine similarity between them, and then select the one that's most similar to the others as the prior subgraph. And the remaining subgraph becomes the posterior subgraph. Next step is prior subgraph optimization. After selecting the prior subgraph, we optimize it by exploring their sketches and its parameters to find the best performing program configuration. Next, when optimizing the posterior subgraph, we don't search all possible sketches. Instead, we focus only the sketch that worked well for the prior subgraph. The final step is code diffusion. Code diffusion is the process of propagating optimized parameter from the prior subgraph to the posterior subgraph. We implemented this parameter propagation as part of Ansor's program initialization rules. In particular, we introduced a case called init-field type size, which sets the parameter per loop split. That is, it divides a loop of a given extent into a smaller chunk based on the split length. The example on the right indicates the original code and the transformed code by the split rule and their parameters named split length. So a loop with extent 1024 is split using parameters 16 and 64. As a result, the inner loop will iterate 16 times and 64 times, respectively. The parameters can be adapted in the following ways. First, if the loop extent is the same, we can directly reuse the split length from the prior subgraph. Second, if the extents are different, we adjust the split length to match the new extent. We select the parameter candidate closest to the prior parameters. Third, we scale the split length according to the ratio between the prior and posterior extent. And finally, for the bias, we randomly initialize the parameters. And these propagated parameters are fine-tuned. This figure compares the prior code and the posterior code, and the posterior code is generated by the diffused parameter from the prior parameters. When we apply parameters to generate code, the posterior code ends up looking very similar to the prior code. For example, they have same or similar loop iterations. This figure compares the relationship between the distance from the prior parameter to the posterior parameter and the latency of the posterior program. As you can see, latency decreases as the parameter distance decreases. So we conclude that there is strong correlation between these two factors. So let me now share the result for our work. We evaluated our approach on both CPU and GPU platforms. For the workload, we used a diverse set of deep learning models. And based on this experimental setup, we compared the compilation efficiency by measuring the compilation time required to find a program with the same latency. Specifically, Ansor's best result is used as the reference point for the comparison. This broad range of experiments demonstrates that our method generalizes well across different hardware platforms and model architectures. This figure compares the compilation efficiency of deep learning approaches of different approaches of both CPU and GPU platforms. To measure efficiency, we look at how fast each method can reach the same performance as Ansor's fast program. We use Ansor as the baseline, and we normalize each value to the 1. And this figure, the X mark indicates that the method did not achieve same performance as Ansor's fast, and a circle with a slash indicates that the method is not applicable to the target hardware. On average, Bayesian code diffusion speeds up compilation time by 2.52 times on CPU and 2 times speed up on GPU. And this slide shows how program execution latency changes over compilation time for both CPU and GPU. As shown in the figure, Bayesian code diffusion was able to discover better programs within the shorter compilation time. Next, I conclude the presentation with a quick summary of the key points. In the beginning of this presentation, we introduced some opportunities in auto-tuning. Bayesian code diffusion helps us efficiently find high-performance code by taking advantages of these two opportunities we discussed. First, it clusters similar subgraph so that we can reduce the search space. And second, it propagates parameter from the prior subgraph to the posterior subgraph in a structured way so that we can reduce the fine-tuning iterations. And in the end, this leads to a much more efficient search process. Thank you for listening to our presentation. Thank you.